All right, guys, we're going to do section 2.1 today, an introduction to limits. And so let's get going. So remember to find the function value. This is just kind of a quick recap of that. You plug this value, f of 1, into the given function, or you look on the graph. So when x is 1, what is the value of the function? So that is an x value, f of 1, that's an x value. So we're going to look and see, find my x value, my horizontal value, here's 1. So what is this value of the function at x equals 1? That value, the y value here, is 0. So f of 4, well, here's 4. So 4, if I go along and find 4, I see that I have a closed in circle here and I have an open circle here. The value, which one would you guess is the one that is actually the value? It's the one that's closed in. So if I follow it along here to the y-axis in between 2 and 4, that would be 3. F of 6, here's my 6. I go down, it's right here, which is at -1. So that's how we find the value of a function. We look and see what is the closed-in circle. Where is the graph at that particular point? But we're going to be talking about limits in calculus. And limit has to do with approaching, not equals. So if you notice this notation, you see that there's a little arrow right here. And so that's not as x equals a, that's as x gets close to a. So this is said the limit as x goes to a, or the limit as x approaches a of the function is equal to some value. So it's what is it getting close to? As the x value gets close to a, what is the y value getting close to? So that is what you're trying, as x gets close to a from both sides, f of x is getting close to the value L. If you're not getting close to anything, or if you're going to two different places, then we would say that the limit doesn't exist. So let's look at this graph. The limit as x goes to 1. Well, if it's just a graph with no weird discontinuities, there's no skips or jumps or asymptotes, it's just the value. So I see 1 right here, there's nothing weird going on there, so it's the function's limit is going to be equal to the same thing as its value, which is 0. What about as x goes to -2? Here's -2, what's my y value here? 3. Now this one, I do see there's something weird in the graph, right? So I have 3. Remember, this does not mean as x equals 3. This means as x gets close to 3. So you're going to go close to 3 from one side. It looks like you're approaching that open circle. And close to 3 from the other side. So if you have your fingers, you're going to zoom in on, from either side, and you approach the x value 3. Are we approaching the same thing? Yes, we're approaching this open circle, which y value is at 3. That's not the function value. If I asked you what is f of 3, you would say 4. But the limit, like what it's approaching, what you guess it would be if you didn't see what else was going on, would be 3, because that's where this line is headed. -2. Now here, at -2, as I come from the left side, I go up here, and as I come from the right side, I come here. Are my fingers going to the same thing? They're not. So we say the limit does not exist, because you're not going to the same value from the left and the right. Now, this is if we're going to find the limit analytically. So here was graphically. Here is, we're going to attempt to plug into the function. So this says, what is the limit as x goes close to -2 of the function -3? I'm going to graph it for you just so you can understand what's going on. Y equals -3 is just a horizontal line at -3. So no matter what x value you are at, what is the y value always? -3. There's no x value to plug in here. So no matter where you are, you're always at -3 because this is a constant value. Now, what if we're taking the limit as x approaches -2 of -3x? Now, if you wanted to graph that, you don't have to graph these. I'm just trying to show you, for those of you that are visual, -3x looks something like this. So if I go to -2, I know that I'm going to be somewhere on this line. How do I figure out where I am? Well, you just plug it in, or the mathematical term for that is substitution. So we're going to substitute in -3 times -2, and negative times a negative is a positive. So our answer would be 6. Let's try this one. This says the limit as x goes to 1. Again, you just substitute it. So we're going to plug in -1 for each x. Being careful, or not -1, it's just a positive one, with signs. So 5 times 1 minus 1 squared. 5 times 1 is 5, minus 1 is 4. The square root of 4 is 2. If you're solving, you would say plus or minus 2, but as it's written in the Radican like this, it just means the positive value. So 2. Now, if I have a fraction, I'm going to plug in the top and the bottom. 2 times 2, 4 plus 1 is 5. 2 plus 2 is 4, so 5 fourths. Okay, now what happens here? This is our trick one, because it's not always that easy, of course. When I plug in 5, let's see. 2 times 5 minus 3, 5 minus 5. I get 10 minus 3, I get 7 over 0. Can you divide by 0? The answer is no. Anytime you have a number over 0, little mnemonic device, remember, no, does not exist, okay? So a number over 0, no, can't do that, it does not exist. And so that's what this says right here. If you're trying to find the limit and you get some number on top here, so you get a value here, that's important. You cannot get 0 because 0 over 0 is a whole other set that we're going to talk about later. If you have a number on top and then you have a 0 on the bottom, then you know it's just no. There is no limit. The answer does not exist. In the graph, there is an asymptote there, a vertical asymptote. So the graph is approaching positive infinity or negative infinity. It's not approaching a value. Now, this is the absolute value function, which hopefully you're familiar with the parent function. The absolute value function looks like a V, like this. Now, the actual definition of the absolute value function is this. This is called a piecewise function. Piecewise because it's like pieces of a quilt, where you took a piece of this function and a piece of this function and patched them together. So the absolute value function is seen as negative x if we're on this side of 0 and positive x on this side of 0. That's why it makes a V, okay? So if I want to find the limit of the absolute value of x divided by x, if I took each of these and divided by x, I would see that it would be -1 if x is less than 0 and +1 if x is greater than or equal to 0, which is what this shows here. Or they just took away the equals. So I have where it doesn't equal at 0, you have an issue, right? If I try to plug in 0, I get 0 over 0, which is undefined. Now, if I'm trying to find the limit as x goes to 1, though, if I try to find the limit as x approaches 1, is there anything weird happening at 1? It's just this line. And what's the value of that line? 1. The only issue you're going to have is if you tried to find the limit as x goes to 0. Then you would say it does not exist because there's this jump in the graph here and your left and right don't match up. But if you're on the left or right side of 0, you would just look at its piece, right? So you're either going to get -1 for all the answers and 1 for all the other answers. So if you're on this side at all, any of the limits would just be this y value, which is 1. And if you're over here, any of the limit values would return this value, which is -1. So I just talked about that does not exist. Now, what if we shift the whole graph? So if you remember horizontal shifts, x minus 3 means you shift the whole graph right 3. So it would be the same exact thing, but just shifted like this. So now at 3, if I try to plug 3 in here, I get 0 over 0, which is undefined. So it does not exist. One-sided limit, this whole thing right here is talking about how you can look from one side. And so if you see this little plus, you see that baby plus sign, that little tiny baby plus sign, you would guess hopefully that plus is usually associated with the right. So that means from the right side. And then this negative means from the left side. And if these are the same, then the limit exists. Okay, so this exists as long as these limits are the same. And if these limits are the same, then the limits exist. That's what if and only if means. It's called a biconditional statement, where a function and its converse are both true. So the limit as x goes to -2 with that little plus superscript, that means from the right. So here's -2, and we're going to get on the right side of -2. The right side is here. So as I'm coming from the right, I'm approaching this open circle, which is at -2. -2 from the left, I'm approaching this open circle, which is -3. And then do these match? No, if these are different, then your answer for this one does not exist. That's what this little theorem up here says. If these are not the same, then your limit doesn't exist. So let's look at this. 1, that little plus means from the right. So you find 1 and you get on the right side of 1. The right side would be here. Then you approach 1. I'm approaching 1 from the right piece. And so what is this open circle at? 2. Then you're going to do 1 from the left side, which is approaching this closed circle, which y value is at 0. Now, do these match? Nope. So this answer is D and E. 3, here's 3. From the left, I'm over here, which is this open circle, which is at 3. From the right, I'm approaching again 3. Do these match? Yes. So the limit will be 3 because the left and the right were the same. Okay, so now for finding them, the limit as x goes to 1. If I just have a polynomial, you still just plug in 1. So that would be 2 times 1 plus 4, so that would be 6. 0, again, I plug in 0 and see what happens. If I get nothing strange, then that's just your answer. So -1 over 1 is -1. Now here's a piecewise function, but I don't have a picture of it. So what I need to think about is this graph right here, it switches over at 0. So for those of you that want to have a visual, this 2x minus 1 is going to be, minus 4 is on the left side of 0 because it says less than or equal to. And this guy, cube root of x minus 1 minus 3 is on this side. So if I'm coming to 0 from the left, am I on the blue piece or the green piece? I'm on the blue piece from the left. So I plug it into that part. 2 times 0 minus 4, so -4. 0 from the right, I would be on this green side. So cube root of 0 minus 1 minus 3. So 0 minus 1, -1. The cube root of -1 is also -1. And -1 minus 3 is -4. Now, are these the same? They are. So what does that mean this limit equals? -4. We were able to discern that you have this limit and it exists because these limits from the left and the right were equal. Now, normally I teach calculus 1 not for business majors, and so just traditional calc 1, and this is where we spend the bulk of our time. So almost always when we're in the other calculus, every time we try to evaluate a limit, we get what's called an indeterminate form. We get 0 over 0. Now, when you get 0 over 0, I want you to remember this. Oh, there's just more work to do. There is a limit, most likely, almost always. There's just more work. You have to rewrite it in a way where you can figure out what it is. One of those strategies is to factor. So most of the time you're going to factor to see what it is. There's a hidden factor you need to remove. And there's a little cheat. The way you figure out what factor it is for those that are not as strong with factoring is whatever x is approaching, you're looking for x minus that thing. Okay, so if x is approaching c, you're looking for x minus c in the top and the bottom. So if I'm going to factor this is a difference of squares. You know, x squared minus a squared factors to be x minus a times x plus a. So if I factor the top, I would get x minus 1 times x plus 1. The bottom is x minus 1. And remember, this tells you what factor you're trying to remove. And so I see I have x minus 1 in top and bottom, so I can say those simplify to be 1. And so this graph actually looks like the graph of x plus 1 and just has a hole in it at this value 1. If I plug in 1 now, I can see where that value is going. 1 plus 1 equals 2. So I turned that indeterminate form of 0 over 0. We plug 1 here, we get 0 over 0. We rewrite it to figure out what it's actually approaching. That value is 2. So anytime you get 0 over 0, say, oh, more work to do. Whereas a number over 0 is no. So let's plug in 0. What happens if I plug in 0? I get 0 over 0, which is, oh, more work to do. Now your factor is x minus this, which is just 0. So on top, we see we have a GCF of x. If I factor out an x here, I'll be left with just 1x. And if I factor out an x here, I'm left with 1. And so now I can see that my x's will simplify to be 1. And I can substitute in 0, and I'll be left with 0 minus 1, which is negative 1. 1 from the right, I still can think about it. If I plug in 1 here, I get, well, first let's plug in 1. I get 2 over 0. Oh, is this O or is it no? This is no, so my answer is does not exist. So you have to make sure you substitute first before you just assume things. If I plug in 2 here, I get 2 minus 2 over 2 squared minus 4. So I get 0 over 0, which is, oh, more work to do. X minus this is what we're trying to factor out. So this one is a difference of squares on the bottom, x minus 2, x plus 2. So these simplify to be 1. And so now I can substitute in my 2. From the left side, you don't really have to worry about from the left unless you have absolute value going on or a piecewise function. So I have 1 over, there's an understood 1 here because you simplified to, or divide to be 1. I plug in 2 for x, so I get 1 over 4. So again, anytime you have that O, 0 over 0, I want you to factor. And the factor you're trying to remove is x minus c. And you're trying to cross that out to see what you're left with. And then you can substitute into whatever you're left with. All right, so this is just limit properties. And most of these things you probably would assume, even though you're not supposed to assume things in mathematics, that can get you in trouble. But if I know that I have a limit of x approaching a of f, and the limit is x approaching a of g, and I know that they're continuous functions, they have limits, they're L and M, then I can add those, I can subtract those, I can multiply those, I can divide those. So it's just, you kind of can substitute in the values for the limits. So let's actually apply this. So it tells me the limit as x approaches 3 of f of x is 2. And then the other one over here is negative 2. So let's try to figure those out. Well, which one are we talking about here? G. So technically I'm doing the scalar multiple rule. I'm pulling out this 5. And I am multiplying it by this limit, which is negative 2. 5 times negative 2, which is negative 10. Okay, but you can just see the G limit is negative 2. So 5 times negative 2 is negative 10. Now here, we're going to do the sum and difference rule. So you're taking the limit as x goes to 3 of negative 3 times g of x minus 5 times the limit as x goes to 3 of f of x. You can pull this negative 3 out here in front if you want to rewrite it. You do not have to rewrite these. I'm just showing you that these are the properties of the limits. Okay, so this is that the limit, if I'm taking the limit of a difference, it's the difference of the limits. And then these multiply, these negative 3 and this negative 5, you can just multiply them times the answer. So essentially, you're just substituting this is 2. And this is negative 2. So what happens if I do negative 3 times negative 2? I get a positive 6. And then I have negative minus 5 times 2, which is going to be 6 minus 10. So you're going to get negative 4. Okay. You could just substitute again the 2 here and the -2 here. You're just allowed to add and subtract limits and multiply them by scalar multiples. So if I substitute in g of x is -2, and one thing to watch out for is only as x approaches 3 is this -2. So make sure we are approaching 3, because every now and then there'll be a trick question where you're approaching something different, and so you have to read carefully. When x is approaching 3, g of x is approaching -2. So basically, you're just plugging in a -2 right here, and f of x is approaching 2. So I have -2 minus 2 over 1 plus 2 times 2. So negative minus a negative, you're actually adding, that's -4 over 1 plus 4. So -4 over 5. And then cube root, and this is our last problem. So let's see, the fifth root. That's 12 times, wait, what's f of x? I think it was 2. Should have looked. F of x is 2 and -2. Okay. This is the fifth root of 12 times 2 minus 4 times -2. The fifth root of 12 times 2 is 24 minus 2 negatives make a plus, so plus 8. So the fifth root of 32 is 2. Because 2 to the fifth is 32. So that's our answer. Okay, so that was our first introduction to limits. So again, kind of some big concepts here is when you're doing a limit, it's what it is approaching. Make sure that you're approaching from the same side for the limit to exist. So like here, the limit doesn't exist at -2. You plug in, you can just substitute to figure out what the limit is. If you get a number over 0, the answer is no. But if you get 0 over 0, you factor to figure out what the answer is. One side of limits, again, they have to be the same from the left and the right for the limit to exist. And then limit properties, you basically just plug in whatever they tell you the limit values are. You can add them or subtract them, multiply them, take the root of them. And so attempt to do your homework. And again, if you get stuck, you can do the get more help feature and choose Ask My Professor.